So I'm very happy to be able to introduce our next speaker, Nadia Polikarpova from UCSD. So Nadia is well known to many people here in the call because she did her PhD at ETH a couple of years ago with Bertrand Meyer, and then moved on to MIT, basically moving mostly from verification to synthesis, what is her kind of main topic right now. And then she became an assistant professor in San Diego. So Nadia is really a rising star in the field. She's won numerous awards like a Sloan Fellowship. She's an Intel Rising Star. She's won an NSF Career Award and many others. So I'm super happy that we have her today in our workshop, and I'm looking forward to her talk. So Nadia, please go ahead.
Thanks, Peter, for a great introduction. I'm really honored to be here today because, I spent some of the best years of my life at ETH as a grad student. And, it's really exciting to be back, even if remotely. So let me start sharing. Yeah, it's hard to follow Myron, but, I'll try to, I'll try to not to bore you too much. So I hope you can see my slides.
Yes.
Okay, great. So let me start by just acknowledging that as a formal methods community, we have come a really long way when it comes to, program verification and developing this, trusted and the dependable systems, right? So arguably the first example of program verification is this paper that Alan Turing published in 1949 that's called Checking a Large Routine. And this paper was about formal verification of a factorial function. And now, some 70 years later, we're actually made a lot of progress, right? And we can build this big, realistic verified systems like operating systems, HTTPS stacks, and so on. However, developing this fully verified system is still very, very hard, right? And there are many reasons for that, but fundamentally, one part why it requires so much effort is that you have to develop one of those systems, you have to write the code, you have to write some formal specs, and you have to write some proofs that the code satisfies the spec. And in this talk, basically, I want to ask the question, what's the next kind of fundamental step for developing verified systems, right? So can we overcome this problem that causes us so much effort? And so one promising answer to this question lies in the program synthesis technology. So program synthesis is sort of a set of techniques that allows you to automatically generate code from high-level specification. And in particular, the kind of synthesis that I want to focus on in this talk is synthesis with formal guarantees, meaning that the programmer is willing to write a formal specification, but in return, we get not only the code, but also the proof that the code satisfies your formal spec, but you want to get this automatically. And of course, this sounds like, a great dream, right? But it sounds almost too good to be true, right? So how do we get, you only have to write the spec, right? So how do you get the code and the proof completely automatically? And in fact, if you try to build a synthesizer that does that, you're immediately faced with two sort of grand challenges. So the first challenge is that program synthesis is a really hard search problem. So if you know anything about program synthesis, and you probably heard about it already yesterday, so what program synthesizers do is they search this really large space of all possible programs in your language to find one that satisfies the specification. And the bad news is that there is usually more programs than there are stars in the universe. And if that weren't enough, the second problem is because we are trying to find a program that provably satisfies the spec, even when we have a program candidate in mind, checking that it satisfies the spec is already a very hard problem, right? That's a program verification problem. And so now you might think, well, am I crazy? I'm suggesting to put two very hard problems together, and I'm saying this somehow is going to make it better. Well, it turns out that if you do your search in a smart way, you can use your proofs to actually help you find the right program faster, as opposed to slowing you down. So in program synthesis, there is this approach called deductive synthesis, where the idea is to, instead of searching for a program first and then trying to prove it correct, you're searching for the program proof in the first place, right? And the hope is that the space of program proofs is somehow more structured than the space of programs, so you can do the search better in a more directed way. So in other words, we want to use our formal specification to guide our search. And of course, deductive synthesis is not at all a new idea. It all started in the 1980s, but recently it has experienced sort of a resurgence thanks to all the cool advances in automated reasoning. And in this talk in particular, I want to focus on one sort of work that I have done with my collaborators in the last couple of years. And this is in particular a work on deductive synthesis of pointer manipulating programs. So think like low-level programs like C programs, right? And so this is important because if we ever hope for synthesis to help us build those dependable systems, right? So many of them are written in a low-level languages like C. So that's why that is useful. Okay, so we built this synthesizer called SuSLik that takes in some specification and produces this low-level code together with its correctness proof. And so if you build such a system, you kind of have two design decisions to make. First of all, how do you want to express the specification? And second of all, how do you want to do the search? And in particular, the challenge of generating C code is that it's usually verbose and unstructured, and it has all these pointers and aliasing that are really hard to reason about. So how do we answer these two questions? So for SuSLik, the answer to these questions actually lies in its name. So SuSLik, apart from being a name of a rodent species in Russian, it is also an acronym for synthesis using separation logic. So if you haven't heard of separation logic, you probably have, but so it's a program logic that was developed by Reynolds and O'Hearn and others in early 2000s. And this logic is specifically meant for reasoning about programs with pointers. So SuSLik uses separation logic in two crucial ways. So first of all, the specifications in SuSLik are expressed in separation logic, which sort of helps it do the reasoning about pointers and aliasing, which is what separation logic is meant for in the first place. And so when it comes to search, so SuSLik is based on this deductive synthesis idea, and it uses a special variant of separation logic as the underlying sort of way of building program derivations and guiding the search. All right, so in the rest of this talk, I will first give you a little taste of SuSLik on a very simple example. I will then talk about how do we generate a little bit more interesting programs with recursion using this cool idea called cyclic proofs. And then in the end, I will tell you how cyclic proofs help us learn auxiliary functions. All right, so let's begin. So my very first, very simple example is, say I want to synthesize a program that swaps the values of two distinct pointers. So how would I write a specification for this problem? So what I want to say in my specification is that is basically what my the state of my memory or my heap looks like before and after executing this program, and I want the synthesizer to figure out how to get from one to the other. So in this case, I want to say that in the start state, I have two memory locations at addresses X and Y, and they store some values A and B. And in the end state, I still have these two same memory locations, but the values are swapped. So I can write this, I can sort of translate this picture into separation logic. So I can write a pair of a pre and a post condition, which are separation logic assertions. In this case, each of these assertions consists of two atomic assertions called heaplets. And in particular, these ones are called points to heaplets. So this one I can read as X points to A, where X denotes the address of the, this heap points to heaplet describes a single memory location with address X and payload A. And these heaplets are joined by a connective called separating conjunction. And the idea, the difference between separating conjunction and a regular logical conjunction is that the assertions on the two sides of the separating conjunction are supposed to hold in two disjoint parts of the heap. So here in particular, in the precondition, we are saying that we're implicitly saying that the two memory locations we're talking about are disjoint. So X and Y are not aliased. And finally, what I want to mention about this specification is that here X and Y are program level variables because they also appear as parameters of swap, whereas A and B are so-called ghost variables. They're only allowed to be mentioned in the specification, and the synthesizer is not allowed to use them in the program. So now we want to give this specification to SuSLik and see what it's going to do. So let me go to my demo. So as you can see, we have a specification here. We can run SuSLik, and then immediately it will give us the program back. Hopefully you can see it. So what this program does is it simply reads the content of X into a temporary variable, and similarly for the content of Y, and then it writes those variables into X and Y sort of to swap the values. So it's a very, very simple, straightforward implementation of swap, which is what we expected. So how did SuSLik derive this program? And you might think, well, this wasn't really impressive because this is a really simple program. But if you think about it, if you think of the space of all possible programs in C with this signature, right? There's actually like an unbounded number of them, because think about it, like, what is the first instruction that I should do, right? So maybe I should read from pointer X at offset 100, right? Or maybe I should do something else silly like that. So the C language and the type system doesn't really prevent you from doing any of those things, right? But your specification and separation logic do, right? So they guide, what programs you can generate. So that's sort of the idea of deductive synthesis. So let me, so the idea behind deductive synthesis is we want to build a proof system that will help us derive our programs, right? And so in SuSLik, we did exactly that, right? So we built this proof system or program logic called a synthetic separation logic. So basically a variant of separation logic that is tailored for synthesis, right? And so what this SSL is basically a set of rules that tell you, if you have this specification, this pre and post condition, which program you should derive from that, right? So more formally, SSL defines this relation over, pre and post condition and program. And the informal meaning of this relation is, if I want to go from a state that satisfies P to a state that satisfies Q, I can accomplish that using this program C. So to give you sort of a sense of SSL, let me show you just a couple of simple rules of SSL, and then we'll see how those rules can derive the swap program. So the first rule, it's our sort of terminal rule or axiom called EMP. So it's basically telling you that if your pre and post condition are both, if you want to go from an empty heap to an empty heap, then there is nothing left to do. You can just do a skip program that does nothing, right? So this is, like I said, our axiom. And then all the other rules, the goal of those rules will be basically to simplify the specification, the synthesis goal, in order to arrive to this state, right, where we just have emp to emp, and we can close our derivation with a skip. So another rule we could use is so-called the frame rule. So the frame rule tells us that if in our pre and post condition we have a part that is the same heap, right, then we might as well solve a simpler goal that just goes from P to Q, right? And if the program C can take us from P to Q, then the same program C will solve the original goal. So another rule we have is the right rule. The right rule says that if in the post condition you have a heaplet that points to heaplet with a non-ghost payload, then I can sort of satisfy this part of the post condition by simply writing E into X, right? And then I will end up with the same X points to E heaplet in the pre and the post condition that can later be removed by the frame rule. And then finally, this read rule says that if I have in my precondition a points to heaplet where the payload is a ghost variable, then I can read out the content of X into a fresh program variable and then replace all occurrences of A with this new variable everywhere in the code. So with this just very, 4 very simple rules, we can already synthesize the swap program. So if you look at the specification of swap, you will see that the only rule that applies to this initial specification is the read rule. So we can use the read rule to read out the content of X into a program level variable, which we called A1. We can do the same thing to Y. Now we actually have a points to heaplet in the post condition where the payload is non-ghost, right? So the payload here is the program level variable B1. So we can apply the write rule here to write B1 into X. Now we have the same heaplet on both sides, so we can frame it out. And similarly, we can apply write to Y and the frame again. And we arrived at our, a very simple goal emp to emp, which we can now close using the emp rule. So you can see how the specification was really guiding what we're doing, right? So we didn't really have too much freedom into which instruction we should synthesize next, right? And so now we are done. We can collect this into one program. All right, so this was a very simple example. So let me show you some more interesting programs, in particular recursive programs. So we'll first talk about how we describe specifications for these recursive data transformations using inductive predicates, and then I will tell you how we actually generate those recursive programs. So our next example would be, let's say I want to synthesize a program that deallocates a linked list, right? And so here in the precondition, I want to say that, well, what I have in my heap is a linked list data structure, right? But I don't want to limit this linked list to a specific number of nodes, right? So I want my program to work for an arbitrary number of nodes. So how do I describe a linked list with arbitrary number of nodes in separation logic? Well, thankfully, there is a construct in separation logic called inductive predicates that allows you to do that. So to define the shape of a linked list, I will introduce a predicate, which I called list, which takes as a parameter the address of the head of the list. And so my predicate will have 2 clauses. The first clause will say that if my head is null, then the list is empty, right? So the whole heap I'm trying to describe is empty. And if the head is not null, then I have a dynamically allocated record of size 2 at address L. And then in this record, I store, in the first field of this record at offset 0, I store the payload. And at offset 1, I store the next pointer. And then finally, at that next pointer, I also have a list, right? So this is what that makes this predicate inductive and what lets it describe a list with arbitrary many nodes. So now that we have this list predicate at hand, we can very easily write the specification for Dispose. So we can say in the precondition, we had a list at address X, and then in the post condition, we don't have anything. It's an empty heap, right? So now SuSLik is forced to get rid of this list somehow, right? So let's see how it would do that. So I have my specification for Dispose here. And so almost immediately, SuSLik generates a program which says, well, if the head is null, there's nothing to do, the list is already empty. Otherwise, I'm getting the next pointer. I'm making a recursive call on that next pointer, and then finally, I'm freeing the head node. Right, so as you can see, this program is recursive, right? So this is how we can deallocate a list with arbitrary many nodes. So again, this was a sort of a very simple program, because in this case, we didn't really care about what is stored in that list. We only cared about its shape, right? But what if we care about the content of the list? So imagine you want to specify something like, please copy this linked list for me, right? So thankfully, inductive predicates are is a very flexible concept, because you can add extra parameters to your inductive predicate, if you want to describe something extra about your data structure. So for example, we can parameterize our list predicate with the set of elements stored in that list. So then we would have to modify our predicate slightly. So here in the first clause, we are saying that if the list is empty, then the set is empty as well. So here I'm showing you something that you haven't seen before. So in SuSLik, our separation logic assertions, apart from the spatial part that describes the shape of the heap, they also have the pure part that is not written in separation logic, it's written in just first order logic, and it just describes some additional properties, right? And this is a well-known fragment of separation logic called symbolic heap separation logic. And so in my other clause, I will have to say that my set of elements is a union of V and S prime, where V is the payload of the head and S prime is the set of elements of the tail. So now that I have this augmented list predicate, I can specify my copy procedure. So by the way, the signature of this copy procedure has an extra parameter for the return location. This is because for simplicity, the SuSLik language doesn't have a return statement. So if you want to return something from a procedure, you need to give it like a memory location where to store the result. So this is what this is. So in the precondition, I can say I had a list at address X with elements S, and my return location stores something I don't care about. And in the postcondition, I'm saying that the list at X is still there. I didn't touch that, but I now also have a list at Y, and my return location stores the beginning of this list. So in the interest of time, I will skip the demo, but I will later give you a URL to play with SuSLik online, so you can try this example yourself. So SuSLik will also generate a recursive procedure for that. Right, so how do we do this? How do we generate these recursive procedures? So let's go back to the Dispose example, because this one is simpler. So we're going to start the derivation with the top level specification. So list X goes to emp. So what SuSLik has a rule that allows you to sort of unfold the definition of the inductive predicate in the precondition. And because our list predicate has two clauses, this would basically have the effect of pattern matching on, whether this list is empty or not, right? So the code that it will generate is a conditional, which basically does the pattern matching, and then it will have two sub-goals. The first one will be for the empty list, right? And this sub-goal is trivial to solve. And the second one is the interesting one, is when the list is not empty. So what can we do with this sub-goal? Well, we see this dynamically allocated record here, so we can use a free rule to get rid of that. But now we end up with this goal, right? So list of Y goes to emp. And so how can we solve this goal, right? So, I mean, we could use open again to pattern match on list Y, but if we keep doing that, this will never lead us to anything good, right? Because our list has an unboundedly many elements, so we can keep doing that forever, never succeed. So intuitively, what we want to do here is to use some kind of inductive reasoning to be able to generate a recursive call at this point, right? So call dispose on Y. Okay, so how do we achieve that? So there are, in fact, a lot of existing synthesizers for recursive programs. And what they do to generate recursive calls is they use reasoning by explicit induction, right? So they would basically, in the very beginning of the derivation, they would say, oh, let me make an inductive hypothesis out of my top level specification. And then now at this point, I can appeal to this inductive hypothesis and make a recursive call to dispose. In SuSLik, we used to do that in the beginning, but now we have like a more general mechanism for generating recursive calls that I'm very excited about, that is based on the idea of cyclic proofs. So cyclic proofs is this generalization of reasoning by induction, where instead of appealing to an explicit inductive hypothesis, in a cyclic proof, you can close an open goal in your derivation by linking it back to an identical goal somewhere else in your derivation, right? And so these links are, of course, not always sound, right? So you can end up with circular reasoning, but there's some global soundness condition you have to satisfy when you're doing this. And cyclic proofs have been used for verification of recursive programs in prior work, right? But sort of in SuSLik, we sort of figured out that, oh, they can also be used really nicely for synthesis. So the idea here is that when we see that we have, so this is our current goal, and we see that we already had a goal in our derivation that looks just like the goal that we currently have, up to alpha renaming in this case. So we can sort of form a backlink back to the root of our derivation. And in terms of synthesis, what this backlink signifies is that it generates a recursive call to Dispose. Right, so this is how we generated Dispose. Okay, so now let me get to like the really interesting part is how this same mechanism of using cyclic proofs allows us to learn auxiliary functions. So this is our last example will be, so let's say I want to flatten a binary tree into a double linked list, right? And so I also kind of noticed that this transformation can be done in place without allocating new memory by just recursively traversing the tree and switching some pointers around, right? And this is true because basically the node of the double linked list and the tree have the same representation, right? There's a payload field and there are two pointer fields. Okay, so how do I go about synthesizing this flatten procedure? So it's very easy to specify this procedure in SuSLik. I can say that in the precondition, I can say that I have a tree at address X with set of elements S, and in the postcondition, I have a double linked list at the same address with the same elements. And this tree and DLL are standard separation logic predicates for binary tree double linked list. And this parameter of the double linked list is the back pointer, which in this case is irrelevant. So in fact, this task is very challenging. So if you give sort of versions of this task to any of the existing synthesizers for recursive programs, including an early version of SuSLik, they will all fail to synthesize this program unless you give them sort of extra help from the user, right? And the reason why they fail is basically a fundamental limitation in the way they handle recursion, right? Because they handle recursion using this explicit inductive reasoning that I mentioned before, and that means that they're unable to automatically discover recursive auxiliary functions. So let me unpack this a little bit and explain why we need the recursive auxiliary here and why these tools cannot do it and SuSLik can do it using cyclic proofs. So by the way, from here on, I'm showing all the separation logic predicates as pictures, just so that it's a bit easier to follow. So this is our initial spec, right? So the very first step that SuSLik and any other synthesizer basically will do is it will pattern match on the input tree. And so this will generate two branches, but the branch where the tree is empty is trivial. So I'm going to just focus on the second branch. So in the second branch, our tree has a root node and the subtrees L and R. So at this point, any synthesizer will can basically perform a recursive call on the left subtree and then a recursive call on the right subtree. But now we end up with the tree elements split between the two double linked lists, right, that we got from the recursive call, whereas the postcondition demands that we need to put them all into a single list, right? And this is where all these other synthesizers face a problem because they cannot solve this goal, right? So solving this goal requires concatenating two double linked lists together, right? Which itself requires a recursive procedure, right? So, and unless the user gave you a hint that, oh, here's a specification for a pen that you can use in synthesis, right? Existing synthesizers cannot do that, cannot solve this goal. However, with cyclic proofs, you can actually do it, right? So let me show you how. So for future reference, let's call this goal G, the one that other synthesizers have problems with. So what will SuSLik do at this point? So again, basically the only thing you can do is pattern match in one of the lists that it has in the precondition. So let's say it starts pattern matching on L. And so again, the case where L is empty is not very interesting. So I will focus on the other case where L is non-empty. Now, SuSLik notices that the current goal looks similar to that goal G that we had before the last conditional, right? So it also has two input lists and one output list, right? Except that one of the input lists is now shorter, right? So this allows SuSLik to solve this goal by forming a backlink to the goal G. And sort of because we are now forming a backlink not to the root goal of our derivation, but to some intermediate goal, instead of generating a self-recursive call, this generates a call to a fresh auxiliary function that we'll call helper, right? And the specification of helper is the goal G, right? So we can see from that specification what helper actually does, right? So it, in fact, concatenates the lists L and R and that node X all together. So after the call to helper, we are left with a spec that is very easy to solve because it has just a single list on both sides. And so now we have solved our synthesis goal. We have no more open goals left, but now we have this sort of weird call to a non-existing helper function in the middle of our procedure. But also we have this goal G that has a backlink to it, right? So what we will do now, what SuSLik will do now is it will extract all of the code that has been generated from G into a separate function called helper, right? And then replace all that code in the original function with simply just a call to helper. So at this point, we are done, right? So we have synthesized flatten with an auxiliary procedure. So, and again, you see the idea of the deductive synthesis, right, was that we didn't have to conjecture the specification for helper out of thin air sort of ahead of time, but the proof led us to abduce the specification for helper sort of on a by need basis without exploding the search space. So let me just quickly show you that I'm not lying to you. And in fact, SuSLik can do that. So here's my demo. Let me start it. And this will take a little bit longer than those previous examples, but hopefully it will succeed. Right, so as you can see, after some 6,000 or so goals explored, SuSLik generates this implementation of flatten that has two recursive calls and a call to an auxiliary, and the auxiliary is right here. All right, so using this cyclic proofs approach, so SuSLik can generate many interesting programs, including nested traversals, programs with non-trivial termination metrics, even programs with mutual recursion. So in total, we have about 54 benchmarks we tried it on with up to 32 statements, and the specs being up to 12x more concise than the code. And all this synthesis takes some reasonable time. So one interesting example that I wanted to show you is that a program that has mutual recursion, right? So this program deallocates a rows tree, which is a variable arity tree that stores its children in a linked list. So for this specification, SuSLik generates a pair of mutually recursive procedures, one that deallocates a rows tree and another one that deallocates a linked list of children, each of which also contains a rows tree. And so we don't know of any previous synthesizer that is able to generate mutual recursion, in particular because proving termination in presence of mutual recursion is a little bit challenging, but with cyclic proofs, we actually get that out of the box. So of course we have limitations too. So we cannot generate all kinds of auxiliaries. So in particular, we cannot handle auxiliaries when they have, when you have to sort of invent an accumulator out of thin air. For example, we can generate a linear quadratic time list reversal, but not linear time list reversal. And in future work, you know, it would be nice to add more rules to extend the class of auxiliaries that we can generate. And another big limitation is that, so, you know, even though cyclic proofs help us sort of abduce these auxiliaries in a deductive way, still sometimes the search space is too large. This is partly because proof search currently relies on some brittle cost heuristics, and it would be nice to be able to learn those somehow automatically, to have smarter heuristics to guide the search, or perhaps combine automatic and interactive synthesis in some cool ways. So I want to thank my collaborators, without whom this work wouldn't have happened. And finally, so here are some papers that we published about this that I encourage you to read if you're interested. And finally, so here is the link. It's SuSLik.programming.systems. This is where you can play with the demo that I just showed you and see the examples of, you know, the rows tree example and the list copy example and stuff like that. All right, thanks a lot. Happy to take questions.
Thanks, Nadia, for a really great talk. Yeah, we already have questions here. So Felix, please go ahead.
Which one?
Felix Linker, sorry.
Okay, thanks. I have two questions. First, a very small one. So you had these two examples using the cyclic proofs, right? And can you point to the difference when your synthesizer decides to recurse and when it decides to create an auxiliary function? Was it just the unsolved proof goal that you still had in the second example?
No, so basically it's always, you know, there is an unsolved proof goal and it always tries to find a way to solve this goal by forming a backlink. However, if the backlink points to the root of your derivation, that generates top level recursion, right? Self-recursion. Yeah. Whereas if it points to somewhere in the middle of your derivation, that would be an auxiliary function.
Yeah, thanks. And the second one is, so how much would you say are these strategies, for example, to generate auxiliary recursion, tailored by your rules? And how much is it like in inner working of the synthesizer that might scale to more patterns that you didn't show us, for example? So did you need to add like manual support for these features that you showed us, or was it something more deeply embedded in the logic? Does that question make sense?
But which features do you mean? Like, did we have to, for example, add extra support for mutual recursion or something like that?
Yes, yes.
So no, so I think the cyclic proof mechanism itself is very general. So for example, we didn't have to add anything extra for mutual recursion. This just comes out of, like, if you think of the shape of your proof derivation, right? So depending how your backlinks, you know, where they go and whether they overlap or not, right? So this is what determines what whether you will get mutual recursion. And so this by itself, like this process of extracting auxiliaries and also the termination checking is really smooth and just works out of the box, right? So I would say where the limitations come from is really from the fact that the only kind of auxiliary specs that you will discover are those that you encounter in the process of your main derivation, right? And because it doesn't really try to invent them on purpose, right? It's just like, oh, I'm just doing a derivation and I noticed that I had some repeating structure in my derivation, right? And so because of that, for example, it cannot discover these non-trivial auxiliaries, right? Because it's not like trying to say, oh, maybe I can reverse a list better if I add another list to my precondition, right? That just doesn't like come up ever in the course of the main derivation, right? So if we wanted something like that, we would need to add special rules to do that.
Okay, thank you very much. Yeah.
Okay, thanks, Felix. And then the other Felix Wolf, please.
Yes, thank you. First, great talk. I have a question regarding termination. If I understand correctly, from what I would expect, since the synthesis of the program is driven by a proof, the generated program should always terminate. Is that correct? Because otherwise the proof would also should be incorrect.
Right. So these are all proven to terminate.
Okay. But this then also would mean that right now the technique is not immediately applicable to some non-terminating system like a server. Is that also correct?
Right. I mean, yeah, I guess you wouldn't want to generate like the top level function of your server this way anyway. But I mean, I think there are other limitations besides termination that would prevent you from doing that, because this technique right now, it's good for like data structure manipulation, because this is what is easy to specify in separation logic. I mean, maybe not so much for things like a server.
Okay, and then my last small question regarding the frame rule. First off, I would expect that there is an additional constraint, right? You can only frame something away if then what you will generate actually doesn't modify something that you have
Right.
sent
So
away.
this is a very good question. I kind of wanted to go back to it. So the frame rule. Here it is, right? So I think there are two things here. So usually the separation logic frame rule has a side condition that says that C should not modify the variables that are mentioned in R, right? So this is not a problem in SuSLik because we actually modified the language so that this is not a problem for us. Our language doesn't have assignment, doesn't have variable assignment. So you can write to the heap, but you cannot redefine the stack variables. So that's why, that's why we use this let syntax for when we read out of the heap, right? So because you can assign to a fresh variable, but you cannot reassign variables. And I think this is a very cool example of something you can do in synthesis, but you cannot do in verification, right? In verification, you're given a language and you're already given programs that people are writing, right? You don't have a choice of like simplifying your language to help you out. So here we're like, I don't care. We are generating the programs, right? So you can, and you can be as expressive without variable assignment, right? So using just heap assignments. And yeah, so we just did the simplification and this drastically simplified our rules. So I highly recommend doing that.
Okay, great. Thank you. Those were all my questions.
Okay, Christoph.
Yes, thank you very much for the very interesting talk and exceptionally clear talk also.
Oh, thank you.
I really enjoyed it. So I have a question about these cyclic proofs as well. You mentioned it that you have to show that the cycles are actually well-founded. And so a general question is how you do that. And then in particular, when you have mutual recursion, whether you can always get away with a lexicographic order of like measures between the different cycles.
Yeah, this is a really good question. So in fact, we don't have to worry about this at all because we're using an existing cyclic prover called Cyclist to do the termination checking for us. So what we do is basically, as SuSLik is, generating these derivations, as soon as it forms a cycle, it basically ships some kind of certificate to Cyclist to check. And so the termination checking in Cyclist is based on some automata theoretic technique, which I don't know all the details of, but basically what you have to give Cyclist is what's called a trace. So you're basically tracing some measure basically along your cycles, right? And this kind of automata theoretic measure that it has actually subsumes not only lexicographic measures, but also things like min, max, and some others. So it's actually very, very expressive, but we get it completely out of the box by using Cyclist.
Okay, so you're building on James Brothers work. Yeah, okay.
Yeah, and
nice.
And Ruben Rose, who's a co-author on the paper.
Okay, and right, and that also covers the individual like progress. So you don't even have to detect how you like individual loops to make progress. That's all handed off to.
Yeah, so we actually don't care at all whether the recursion is mutual, whether those things overlap or not. We're just like, we have a derivation, we make a trace, we ship it over, Cyclic tells us whether it's okay or not. I don't know how it does it, but it works great.
Okay, that's nice. Thank you.
Okay, Malte.
Yeah, also thanks from my side for the very nice talk. I was wondering, in specifications for more complex examples, we typically use abstraction functions, abstract over the data structure as it is in memory by a set or a multi-set and so on. So I guess then for SuSLik, this means that the specifications don't talk about the heap directly, as they, I guess, currently do with either a raw separation logic formula or a predicate, but they specify the changes in terms of the abstraction function, and then going through the abstraction function, so that as a human tells us, okay, and this is how the effects relative to the abstraction function could be translated to memory then. I don't know, do you support this currently? And if so, how well?
Well, I think this is already kind of what we show, right? So because the so I mean, you define those inductive predicates, which defines your abstraction, right? So for example, we have this list predicates parameterized by a set. So now your set is your abstraction of the list, right? And as a programmer, you are writing your spec in terms of those sets. So here, maybe it's not very interesting in copy, right? Because in copy, you're just using the same set everywhere. But imagine something like you want to synthesize append, right? So then you would say, I have a list at X with elements S1, and I have a list at Y with elements S2, and I want a list at Z with elements S1 union S2. Right, so you're basically expressing your spec in terms of the set union, and then the predicate is what maps that back to the actual memory. Does that answer your question?
Yeah, I guess the follow-up with that question then would be: is let's say the ghost data structure, such as sets and so on, is it fixed, or can the user extend that?
So currently in SuSLik, it's fixed. So the idea is in SuSLik, we're using an SMT solver to discharge those proof obligations over the pure formulas. So we have, like, we're using a fixed set of theories. You just allowed to use linear integer arithmetic and like theory of arrays to encode sets, because we want these proof obligations of the pure formulas to be SMT decidable. So I can, of course, extend it with other like SMT decidable things, right? So I can add, for example, maps or multisets. There's no currently easy way for a user to add them. That would be great, of course.
Okay, thanks. And I have another question. So you're currently using it for synthesis, and if I look at the triple you showed, P is replaced or is transformed to Q by some command C. Then I guess what you have is P and Q are given, and you are searching for C. Do you think it's feasible to do it the other way around and to infer specifications? So you have C given, but you don't necessarily have P and Q. You think that a similar approach would work for solving that problem as well?
Similar approach. I'm not sure about similar approach, but I think that, there are tools that do specification inference like that, right? Like infer, that I guess what it does for a living, right? So we are specifically solving it the other way around. How similar the approach is, I'm not sure. But I guess all of these problems like verification, inference, and synthesis, they're all eventually based on a very similar set of rules, except that depending on what's given and what you're searching for, you would sort of write your rules slightly differently so that they can guide you in a different way, right? So for example, if you look at the right rule in syntactic separation logic, right, that's a very different rule than the right rule for verification in separation logic. But how is it different? Well, basically, the regular separation logic right rule would just tell you, oh, I have an X points to something heaplet in the precondition, and then I can write. I don't care what's in my post condition, right? So here in SSL, we have to say, no, I mean, if we don't care what's in the post condition, then we don't know what to write, right? So our right rule is like, well, please look at the post condition and see what to write. So I think this is how, the rules will be slightly different depending on what you have given and what you don't have.
Yeah, that makes sense. The reason I'm asking is because I really like the fact that you can synthesize auxiliary functions, which I mean, seems almost like too good. And my feeling is that this relates to the problem of finding lemma function applications when you synthesize specifications, because there often you have a specification and the sort of adjacent specification doesn't immediately follow, but you need a more complex ghost code, for example, to transform one into the other. And this at least vaguely seems related to the fact that you can synthesize auxiliary functions.
Right. But I think we cannot.
Sorry, let me just step in here because we are really running out of time. So
okay.
I would suggest that we take the other questions in the chat. I hope, Nadia, you can still be around for a bit. And sorry if I need to cut the others off, but we already used up almost the entire break.
Sorry.
No, it's great that people are so interested in your talk. I mean, it was a fantastic talk, and it's not surprising that it sparks a lot of discussion. So, but anyway, we're running out of time. So thanks again, Nadia, for a really nice talk. And yeah, let's continue the discussion in the chat. And I would suggest we take a 5-minute break and we continue like 2 or 3 minutes past 7 with the next talk. Thank you.